Okay, so now we'll move to time-based voltage regulators. So we have seen so far like how the analog converter works, and then we looked into digital, very basic digital, because in this course we don't want to cover the whole design, but we just want to give you the basic idea how digital is designed, just like we did in the LDOs, very basic concept. So for any regulators, if you know that I mean, what are the requirements? Obviously, the high power density, and which means higher efficiency due to reduce heat dissipation. So whenever you are looking for high power density, one thing is important, that you have to achieve very high efficiency, because when efficiency is poor, then it's very difficult to achieve higher power density. And sometimes it may even require heat sinks, which will actually increase the size of your module. So smaller passive components to reduce board space, because I mean, I don't want my inductor to be that big, okay, and this is your chip, converter chip, and you can see that most of the area is taken by your LNC. So shrinking die size by innovative controllers and integrating more features on a single PMIC means, let us say, I don't want my controller to occupy more area than compared to your power FET. I want my power FET to dominate area, because I am looking for lower RDS on. But if your, let us say, controller becomes 2 times of our power FETs, so that is very impractical actually. So we always try to minimize the area of the controller, so that you are only limited by the power FET, your chip size. And by reducing the size of the controller, if let us say I want to achieve 2 millimeter by 2 millimeter die size, and which means if I reduce the size of the controller, the extra space I can use for power FET itself, and I can put some more FETs to reduce RDS on further. Stable supply, which means high performance controller design, and we know that transient response and your output accuracy, everything depends how good is your controller actually, your error amplifier, your compensation. So if you look at technology trends in PMIC, so and we know that semiconductor process has been scaling. I mean, almost every year you get a new process, and I mean, if you look at like maybe 10-15 years back, we even more than that actually, 20 years back we were at 0.5 micron, then maybe after 5 years or so you got 0.35, and then 0.18. I mean, it has been here for more than a decade, 0.18, and we still use this 0.18, because all the features which were available here, like a high voltage devices and everything. So and these days when you look for 0.18 high voltage process, you get these devices also, 0.35 and 0.5. So this will be running at 3.3 volt, 0.5 will be running at 5 volt. So and 0.18 will be running at 1.8. So you get different variety of devices in the same process, so that you can do all your logic in smaller channel length and all your high voltage in the higher channel length. So you can, on the same substrate, you can have multiple devices. And if you have a BCD process, you can even have 40 volt, 60 volt devices actually. So low parasitic packaging technologies. So I mean, old days what you use on your breadboard is a dip package actually. Then we have SOP and then QFN. So basically, as you move in this package on the right hand side, you will see the parasitics will reduce, because the package parasitics is mostly driven by the how the lead frame is done and how the pins are actually. So bigger the package means more parasitic, package bigger and your die size is much smaller. So you have to use a longer bond wire to connect your pads to pin. So and this WLP is nothing but wafer level package. So these balls actually will sit directly on the die pad. So your die size will be same as package. So if let us say I remove the package, then your X and Y dimension of that die will be same as your package. That is why we call it wafer level package. So this package can be done at a wafer level, and then you can slice it actually. But these packages cannot be done at wafer level. You have to first slice your die and then send it for packaging. And So most of the time this is maybe 4 to 5 times bigger than your die, these packages, other packages. So among these three, the QFN is the best, and but if I have a WLP option, then nothing is better than that, because your parasitics will reduce. So think about you have these power FETs, and these power FETs are connected to ground and VDD. So I don't want to add any inductor in the series, because these are carrying like very high switching current, and current is rising from 0 to few amps within no time. So your LDI by dt noise will increase if you have any series inductor there, and that will kill everything actually. So you cannot have more than few hundreds of picohenry inductor. But if you have any bond wire, you can easily get a like a 1 or 2 nanohenry, and that will kill everything, especially if you are doing very high current converters. So from parasitic points of view, this is the best, and also from size point of view, because your package is same as die size. So these packages are available, and most of the PMIC which going in the cell phone and other devices, you will see they mostly use WLP package. So and you can see here, in fact, so this is your Galaxy S8, and this is your PMIC, this guy. So this Samsung phone, this is Qualcomm PMIC actually, PM8998, and at the bottom, if you flip upside down, what you will see exactly these balls. And this is much bigger PMIC, because it has integrated, let's say 5 to 6 switching converters, then it has more than 25-30 LDOs inside. So you have a lot of power supplies inside, and then other than that you have a lot of housekeeping stuffs like ADCs, everything for measurement. So it's like more than 200 pins PMIC, you can say. So now if you see, this PMIC is surrounded by these passive components, and these are nothing but your inductor and capacitor. So these bigger size you see, they are mostly inductors, and smaller sizes are capacitors. So almost like I think 2/3 of the total area is taken by your passive components. So which means this is not the limitation. This chip is not limiting your module size, but it's a passive component which is limiting your module size, and mainly because of we are using WLP package. So the chip size is very small. So which means our target should be to reduce these passive components, not to reduce the die size further, because we won't get any benefit. Even if I make it 0, still the almost 65 to 70% will be occupied by the passive component. So it will not help much in that case. So for the same ripple, we know this is the formula. So if I want to achieve the same ripple and increase the frequency, let's say double the frequency, I can reduce the size of inductor by 4 times. Okay, or I can reduce inductor by half and capacitor also by half. But most of the time capacitor are much smaller compared to inductor. So we always try to reduce the inductor size actually. You can see, like if you are running at 1 megahertz, your 4.7 microhenry inductor will look like this. I mean much bigger than combining the capacitor and your chip size. Then 4 megahertz, it's 1 microhenry if you are using. Then, and once you go to 8 megahertz, you will be using maybe 0.25 or half a microhenry. I think 1/4 most likely. Every time you double, basically you can do 1/4 of the inductor size. So at 8 megahertz, you can hardly differentiate between your capacitor and inductor. So that's the reason, like we want to push our switching frequency as high as possible, so that we can achieve a smaller passive size. But there are some limitations, and we know with the analog controller, if I want to increase the switching frequency and I want to still operate at 110 bandwidth, I need a very high gain bandwidth error amplifier. I need a very fast comparator, because I cannot have large delay here. Then basically that will limit my duty cycle if you have a large error. So same thing with the RAM generator, you require a reset. So reset will require some time, and that time has to be very small compared to your switching period. So when you are increasing, let's say I am running at 100 megahertz, then I cannot have 1 nanosecond reset time. It's almost, it's 10% of your total time. So it should be a very small fraction, let's say even much less than 1%. Comparator again, so which means everything will contribute to your area here. So significant power penalty you have to pay at high FSW. Then if you going for digital controller, we know achieving a high resolution. So ADC, let's say you want 10 bit, and we talked about two cases where in one case you can limit the range of ADC, but let's say I am looking for full range, then designing that ADC with such a high speed, because I want my ADC output to be available within one cycle. So you have to run at very fast, and if you are looking for let's say 100 megahertz kind of DC-DC converter, then the bandwidth of ADC should be much high. Okay, so you have to incur a lot of area again in the ADC, and if a number of bit is increasing, then it becomes even more difficult to design very high bandwidth. And the DPWM, again, let's say you are using DLL, then it's dependent on inverter delays, and if I want more resolution, then delay of each inverter should be very small, and then your inverter should be very fast, and which means it will take lot of basically area and power. So you are increasing the size of your inverter to make it fast, okay, which means you are increasing the power as well as area. So again here significant power and area penalty you have to pay. So then in the time based, what we do actually, so we know I am only interested in PWM here, and PWM is nothing but time signal. I am not interested in the level of this, level is getting converted in the power fed. So I am only interested in the time information here. So instead of, let's say, you take the error signal in a conventional, so you can either, if you are using analog, you will processing in analog the voltage signal, or if you are using digital, then you will convert to digital and then process it. So in both the cases you are doing either like digital processing or voltage processing, and then you have to convert that into time by using PWM modulator. So what we are doing here, upfront we are converting into time, and we will process everything in time, and my resultant will be time. So I don't require any PWM modulator here. So we got completely rid of the PWM modulator. So it has saved me a comparator. I don't require any RAM, and there is no delay associated with that. So I can run at higher speed also. So that's the main advantage. Now I can push it, and now it's dealing in the time, not in the voltage levels, because I am processing in time. So I can run it at any voltage actually, because I am not. But if let's say, can I design an op-amp which will run at 1 volt? It's very difficult. If I want to achieve very high gain, you have to do cascade or gain boosting, and it will limit your swing. So your devices may go out of saturation, and it will kill everything. But here it's just a time. I am interested in delay, so I can run at a lower voltage, and we can easily scale with the process also. So that's the advantage of this. So basically this, if you look at after converting to time, it's looking more like a clock, and clock is nothing but a digital signal. So it looks like a continuous time digital basically. So it preserves the benefits of both analog, which is low power high accuracy, and digital, which is process scaling, low voltage operation, and area efficient. And so we'll see that when we process in the time domain, we don't require any capacitor actually. So let's say for the integrator we required a very large capacitor. Here you don't require that capacitor at all. So all those PID compensator can be designed without using any R and C, or very small R and C in some cases you may require, maybe order of 1 or 2 picofarad only, not just like more than 50 picofarad or 100 picofarad we saw in the other case. And it has implicit PWM generation, so it doesn't require any PWM modulator. So we are minimizing the delays associated with your comparator, as well as the reset time which you require to reset your RAM. So it's highly power and area efficient. And so we know oscillator, voltage controlled oscillator. So omega is d phi by dt. So if you want to calculate the phi, it will be integral of omega. So if you give any change in the frequency, it will be integrated into phase, and if I am using voltage controlled oscillator, then frequency is proportional to voltage. So any change in the voltage will get integrated into phase. So if I am looking a phase transfer function, which means phase divided by your input voltage, it will be KVCO over S. KVCO is the gain of VCO. And people who basically are taking PLL, or when you take PLL, you will understand this even better actually. So KVCO over S, and when you model the PLL, you model the VCO as integrator actually. So the VCO is acting as an integrator. So this simply are like 3 inverters connected back to back. Here output and input is shorted. You get a ring oscillator, and if you can make it a current controlled or voltage controlled, whatever, it doesn't matter. So you get an integrator, and you can control the gain by controlling the KVCO. So without any capacitor, you can get the integration function here. So, and in the PID we require proportional, integral and derivative. So now, so this is showing the time behavior. So just to explain how it works. So let's say this is my step signal, input is step signal. So when I give a step signal, this clock VCO frequency will change, and if I compare with it with a fixed reference, then I will get the output nothing but more like a PWM, because cycle by cycle phase is integrating. So every cycle your phase difference between the reference clock and this VCO clock will keep changing, and that will get translated into a pulse width. Okay, phase difference is nothing but a pulse width. So what you get here is the duty cycle output, that's it. And this is how your phase gets accumulated actually. So let's say this is free running frequency of this VCO is 10 megahertz, okay, which is 2 pi into 10 mega radians per second. And so, and if KVCO is 2 pi mega radian, which is 1 mega 1 megahertz per volt, or 2 pi mega radian per second per volt. So the phase difference will become 2 pi every 10 cycles. Okay. So the KVCO will define how much phase will change in one cycle actually when you give the step at the input. So every 10 cycle your phase will become 2 pi, and then again will start. So we want to avoid this condition. Let's say I am looking maximum you can get 100% duty cycle, but the moment you go to 2 pi, it will again go to 0 because phase will fold back. So that is the problem with this actually. You don't allow to go more than 2 pi, otherwise duty cycle will get reset and your output will die. So because we don't want, we always want our duty cycle to saturate it to 100%. So this is called actually cycle slip, which happens in the PLL. So and in converter we call it duty cycle slip, because this cycle is corresponding to a duty cycle here. So every 2 pi it will, so which means your converter should settle before it goes to 2 pi, otherwise you will get a cycle slip, and at the output your, I mean regular, it will go completely out of regulation. So how we fix that, we have some techniques, we will tell you later. So now if I compare the op-amp RC and time based integrator, so we know that op-amp is a fully differential at the input actually. So differential input and single output ended output, and so if I have a RC, so the integral gain will be 1 over RC, and if I give a, let's say, square wave at the input, I should get a triangular wave at the output. Now I can have a 2 VCOs, one is connected to V in, other is connected to Vref, which is this guy. So you can think about, this is a positive terminal and this is the negative terminal. Now this VCO will give me clock ref, this VCO will give me clock, and this is fixed. So reference is fixed, and this is changing variable, so this will vary accordingly. Now I have a phase detector which will give me the difference between the two phases, and now I get a PWM and pass it through a low pass filter. That PWM will get converted to your DC or low frequency signal. So this filter should have a very low cutoff where we can filter out all the ripples at PWM, and we can get only the signal frequency. So if I put a, let's say, box around this, I mean input and output, So let's say this filter is good enough to filter all the ripple. You can hardly differentiate between these two. So both functionality will be exactly same. Okay. So the reason we use a VCO here, because if I use a, let's say, feed it directly a clock ref, then with the process voltage or temperature, this VCO will change. So you will not get the same thing in that case. So we want this guy to track this guy, correct, so that we can get a, so whenever V in equal to Vref, no matter what is the VCO frequency, okay, both will have a 0 phase when these are 0, provided that your VCOs are matched. You cannot have a different K VCOs, otherwise you will get an offset. So now this is, we can easily convert the same thing to type 1. In the type 1 we know the compensator is nothing but integrator. So simply you put two VCOs, one is is fed by Vref, other is with the feedback. And so now if there is any difference between the Vref and V out, that will get converted into a phase difference and will accumulate and will change the duty cycle. So the only condition these VCOs can have a same frequency is when Vref equal to V out. Okay. And if I want Vref equal to V out, the duty cycle here should be corresponding to V out over V in. Okay. Let us consider no loss, even in the, it is a feedback, so even loss it will compensate for that. So which means it will always lock in frequency, and I am not locking the phase here. One thing you have to remember, I am only locking the frequency. So phase is free to go anywhere, because I want different duty cycle. If I lock the phase and make the phase difference between this 0, then I will always get 0% duty cycle, which won't help me. Okay. So that is why I do not want to lock phase, but only lock in frequency, so that my phase is free to go anywhere and it will always lock at the duty cycle, which will give me the desired output or V out equal to Vref. So this will be your D. Now D you can relate with the phase difference. So the phase difference between 2 divided by 2 pi will give you the duty cycle, just like we do T on over T on plus T off. And in voltage domain, your duty cycle is nothing but V out by V in. And if you have a voltage controller or analog controller, your duty cycle is V control over Vm, correct. So you can assume here this phi control minus phi ref is nothing but it is phase representation of your V control in phase domain, and 2 pi is representing your amplitude of your Vm. Here amplitude is of the phase is 2 pi actually. So everything is now you are looking in the x direction rather than y direction. So type 1 is easy, we only need VCOs, but now if I want to do PID, then for PID we need both proportional and derivative. These two component extra we need, and integral we already know how to do it. So we need to implement time based proportional and time based differentiator. So proportional is just like we have VCO, we have VCDL, voltage control delay lines, where your delay will be proportional to V in, and delay is nothing but phase. So there the phase was integral of input, here phase is directly proportional to input. So it is looking more like a gain, V out equal to K times V in, here phi out equal to K times V in. So if you look at a transfer function, it will be only gain of this VCDL, which is K VCDL. So you will get a flat curve. So but doing a derivative component is not easy. So what we do actually for derivative, we simply put a first order low pass filter and use the same VCDL. So if the RC time constant is small enough to push that pole outside, so it will behave like an differentiator, correct. So your pole is outside UGB, so you will get only S term, the numerator, denominator is out of picture. So then VCDL will give me the gain, so I can use it as a derivative component and it will give me this kind of behavior, basically the pole 0 at origin, just like integrator gives me a pole at origin. So which means high pass filter plus VCDL acts as an V2, ideal V2 voltage to phase differentiator. So now we have all the three components, and we know that delays are added when you cascade them. So adding them is not difficult, just keep cascading. So this is my integral. Now VCDL1 is the proportional then with the high pass filter another VCDL give me the derivative component. So the output will be, so if this is a phi I, this is phi p, phi I plus phi p, because input to this is phi I. So input to this is phi I plus phi p, so output will be phi I plus phi p plus phi d. So this phi control will have all the three components: integral, proportional and derivative. Now you can use this again, the reference VCO with the Vref, and it will, the loop will, the feedback will force always to get the duty cycle to give me the desired output. So the only thing now you have to decide how you design this VCDL and KVCO, so that you can place your 0 and make your loop gain according to your requirement. So which means first we have to do voltage mode. We know how to design the voltage mode, where to place the, because from here it is very difficult to say where is the 0 and where is the pole, but here we can easily tell, correct. So what we do, we first I mean always we look in terms of poles and zeros, we never look at in terms of Ki, Kp and KD. It becomes very difficult, we cannot understand that until unless you know the 0. So those zeros can get converted to, and we know how to convert that, the proportional in terms of, or integral and derivative component in terms of zeros. So this was the, if you remember, this was the equation we came up with earlier. So once we don't know those zeros, we can easily calculate Kp, Ki, Kd, and we have already, and I think we discussed this, how to break this into those three components. So you have to basically ignore the pole and divide by S, so you can get that Ki, Kp and Kd, all the three terms. So we know the Ki, Kp, Kd in this, and we know Ki, Kp, Kd in this, and all we have to just relate this one with the other, equate, and we will get KVCDL equal to, so in time domain your proportional is nothing but KVCDL, and Ki is nothing but KVCO, and Kd is KVCDL2 into RD CD, which is the high pass filter actually. And in voltage domain, in terms of 0, this is this, and if we equate them, we know omega Z1, omega Z2, we can calculate KVCDL and KVCO and RDCD. Everything we can calculate and map to that, and model in frequency domain and design whole thing.